In this lecture, we are going to assess the quadratic functions. So this is similar to what we did in the linear functions, in that we are going to investigate the quadratic functions deeper, in detail. Okay? So similarly, with respect to the linear function, we also have a parent function for our quadratic functions. And the most basic of our quadratic functions is the one that you see on the first column, the second box on the first column, y is equal to x squared. Okay? And y is equal to x squared is actually illustrated by the first graphical pattern that you see below it, below the parent function. So the general equation of a quadratic function is normally the one that you see here. It is y is equal to ax squared plus bx plus c. So as you notice, we have a, b, and c, and these a, b, and c are elements of real numbers, so they are all real numbers. Okay? And they are constants, so they are the coefficients, the numerical coefficients of your variable x. And depending on the vertex or on the translations of your quadratic function, then you would get a graph that is similar to what is below the general equation form of your quadratic function, which is in here. So the example here is y minus 3 is equal to 0.4 x minus 1 square. And this is actually written in the vertex form. So this is written in y minus k form is equal to a x minus h square. That's the vertex form of the quadratic function. So the vertex form is in the form y minus k is equal to ax minus h square, or could be taken also as y is equal to ax minus h square plus k, because you transpose your k here, it becomes positive. It becomes positive k, but they still have the same vertex h and k. And the transform function of your quadratic function is equal to y minus k, the one that I just discussed. It's y minus k is equal to ax minus h square, and that defines your vertex hk. But in terms of translations and dilations, you could notice that your quadratic function is dilated with a factor of a. It's a vertical dilation with a factor of a, so vertical dilation. And what else? You also have a horizontal translation. So horizontal translation to the right. H units right. Okay, what else? We have a vertical translation. Vertical translation, k units up. So this is the basic of the transformation of the quadratic function. So as you notice, the graph of a certain exponential, a certain quadratic function changes according to the sign of your a. So let us investigate these functions, these quadratic functions, in terms of graphing them. And we are going to do that on the next page. So this is our next page. First, let us investigate our y is equal to x squared. And we are going to need a table, of course. So this is a given, okay? We're plotting our y is equal to x squared in terms of a table. Although the vertex form or the vertex could also be used in graphing them. And that's one way of graphing a quadratic function actually, to get the vertex and then to get also the values of your a. But in this case, to accurately define our quadratic function, we would use the table formula. So the table method gives us our x value and our y value for specific values of x. Let's say, for convenience, we again choose our x's as from -2 to +2. So we get rid of the other boxes. We don't need them. But just in case that you want to expand this, then you could do it. You could do it from -3 to +3 or any interval you want. Now if our x is equal to -2, you notice that your y is just x squared. So anything that you place to your x here, this is y is equal to x squared. Then let's say you change it with a -2 value, then every number that you put in for your x would always be equal to a positive number, which is square. So this is +4. And if you insert -1, it will be 1. 0, 1, and 4. Okay, so I don't need this anymore. Okay, so now we're going to plot the points, my points, of course by the help of the grid lines. So setting in the axes, we have y-axis and x-axis. If my x is -2, then my y is +4. So is +4 accommodated for y? Yes, it is. So we have to plot the point there. If it's -1, then your y is 1. So it's here. And if your x is 0, then your y is also 0, making the origin also part of your points, your pair of points. And then 1, 1, and then we have 2, 4. Okay. Now we have to graph the equation. We'll make use of our arc. Let's see if it coincides. Okay, so it doesn't. Okay, let's just make our own arc just by drawing an arc for the points. So I am drawing an arc connecting all the points. This should be a smooth curve, okay? So this goes here, it transcends throughout your x positive or negative infinity and y positive infinity. So now I took off the grid and let's take a look at the property of y is equal to x squared. Now you would notice that your y is equal to x squared has an opening which is upwards. It opens upwards. So its concavity is concave up. Okay? When you say concave up, it opens upwards. So it's concave up. And at this point, you have a positive slope. It goes like that. Okay? And at one point, let's say this is A, and this is B. So at point A, or at the portion A, okay, you have concave up, and it is positive. This slope is positive. Now, on a portion of B, it is still concave up, but now this slope is negative until it reaches its minimum point, which is at 0, 0, wherein your concavity ends. Okay? So that's how to graph your y is equal to x squared. Now, in quadratic functions, the variable with the power of 2, in this case, this is x squared, has a coefficient a, which should not be equal to 0. Because if your a is equal to 0, then we have nothing. I mean, y is just equal to 0, which is just your x-axis, right? Am I correct? So let us investigate further the general equation, or the general form, which is equal to, what is our general form? Let us take a look at here. So our general form is ax squared plus bx plus c. So let us write in here. So y equals ax squared plus bx plus c. Again, in here, your a, b, and c are all real numbers. So they are element of real numbers. Okay? When you see element of real numbers, they are all real numbers. No imaginary numbers. What else? What else do you see there? Your a should not be equal to 0. Because if your a is equal to 0, then you would have 0x squared plus bx plus c, which will give you a linear function bx plus c only. Okay, so that is one of the characteristics of the general equation of the parabola or the quadratic function. So anyway, by the way, the graph of a quadratic function is called a parabola. Okay, for the Greek word meaning along the path of a ball, because a ball could be kicked and it would give you a projectile motion, which is curved. It's curved in nature. So in illustration, if this is a ball and you kick it, this is your feet. Okay, let's say this is your feet. Then this ball will somewhat form a pattern, a path, which is curved in nature, and that's what you call parabola. It's the trajectory is what you call a parabolic curve. Okay, so that's where the coin parabola came from. So let us erase this. We don't really need this much. Okay, where are we now? So we are graphing the equation y is equal to 3 minus 0.4 x minus 1 squared. We could solve this using the vertex form. And what is our vertex form? Our vertex, or let us use first the, what do you call this? Let us use first the dilation translation method. So you can see that this graph here, or this equation here, y is equal to, let's create a boundary here. Okay, y is equal to 3 minus 0.4 x minus 1 square. You can see that it has a vertical dilation, which is negative 0.4. So dilated vertically, vertical dilation, negative 0.4. That's also equal to 1 over, negative 1 over, that's 0.40. So 2 over 5, am I correct? So negative 2 over 5. And we have a translation, an x translation. So x translation of positive 1. So 1 to the right. And what else? We also have vertical translation. So vertical translation, which is 3 upwards. So our equation here now is how do we get the dilation, which is 2 over 5. So you can see that your origin, in this case, is moved to a vertical translation of 3 up and a horizontal translation of 1 to the right. So taking note of those characteristics, we have 3 up, so 1, 2, 3, and 1 to the right. So it means that it went here. Am I correct? The vertex went here, 3 up and 1 to the right. So it would be there now. What else? It is negative 0.4. So it is reflected across the across the x-axis. So it's a vertical reflection across the x-axis with a dilation factor of 0.4 or 2 over 5. So that means that it's going to look like this. This is so thick. Okay. So it would look like this, okay? It would be inverted because it's a vertical reflection. Okay. Now for simpler purposes, we could just get our x-intercepts and y-intercepts. And how do we get our x-intercepts? To get the x-intercepts, we set y is equal to 0 and solve for x. So let's solve it with y is equal to 0. So 0 equals 3 minus 0.4 times, I need a bigger space. Okay, let's do it below. So y is equal to 0. So that gives us 0 equals 3 minus 0.4 x minus 1 square. And that would give us 0 is equal to, or let's transpose 3 now. 3 is equal to negative 3 is equal to negative 0.4 x minus 1 square. So we have 3 over 0.4 is equal to x minus 1 square. So that would give us 15 over 2 is equal to x minus 1 square. And then we square root both sides. Will give us positive or negative square root of 15 over 2 is equal to x minus 1. So our x is equal to 1 plus or minus square root of 15 over 2. And 15 over 2 is just 7.5, so we take our calculator here. So 17.5, or 7.5, I'm sorry, square root, it's 2.74. So approximately x is approximately 1 plus minus 2.74. So x is approximately 3.74 or negative 1.74. So it's somewhere 1.74. So it would be negative 1.74. I'm sorry. This is negative 1.74. So where is negative 1.74? It's somewhere here. And the other one is 3.74. So it should be somewhere here. Okay. And how about our x-intercept or our y-intercept? I mean. Okay, let's solve for our x-intercept. Let's take out the grid first, okay? Okay, where is our y-intercept? So x is equal to 0. Set x is equal to 0. And that will give you y is equal to 3 minus 0.4 times 0 minus 1 square. So that will give us 3 minus 0.4 times negative 1 square. So y equals 3 minus 0.4. That will give us a 2.6. Am I correct? So let's have the grid again. It's 2.6. So somewhere here. This is 2, so it should be somewhere here. Okay, that's our y-intercept. And now we are ready to connect all of the points by drawing our parabolic curve. Okay, what is this point? This point is the translated, the vertical translation and the horizontal translation combined. So what is this point anyway? This point is the vertex, and the vertex of the parabola that we did is actually 1 and 3. So we have a vertex of 1 and 3, and its axis of symmetry is your x is equal to 1. So this is the graph of our quadratic function. Y is equal to 3 minus 0.4 x minus 1 square. Okay? So let us investigate this graph then. This graph has some properties which the first graph, the parent function, does not have. So first of all, its concavity is like that. So its concavity is downward, so it's concave down. And let us say this is the portion A. This side is the portion A, and this is our portion B. What can you say about our portion A? Okay, for our portion A, we could see that the graph is still concave down, but the slope is decreasing. I'm sorry, it's like that. Okay, so it's still positive, but it is decreasing. So positive and decreasing. Okay, now for B, you could see that the graph is also concave down, but this time your slope is it's negative, and it is also decreasing. So negative and decreasing. So that is the graph of the quadratic function y equals 3 minus 0.4 x minus 1 square, as it is originally seen with the general form. So of course, we are now ready to tackle the other graph, the letter C, y is equal to 3 minus 2 times x minus 1 square in terms of its transform functions. So let's do it on the next discussion.